When you hear about knots, various things may come to your mind, so I'd like to start with mentioning that I mean knots which you can make on a piece of a rope. It turns out that this kind of simple activity gave rise to the whole field of mathematics. And of course, we meet such knots everywhere around us, like on a piece of a rope, as I mentioned, on a piece of a wire or so. In nature, in art and culture, they are a very popular topic in arts and culture. But also it turns out that they play a very important role not only in mathematics, but also in chemistry, physics, and in biology. So in the maybe second part of my talk, I'll try to say a few more words about physics and also biology. But to start with, I will say a few words about this mathematical, a branch of mathematics which is called knot theory. So more precisely, knots are curves in some three-dimensional space. And first of all, they have to be closed, because mathematicians would like to define them somehow uniquely. So if you have a piece of a rope which has open ends, then you can untangle it somehow easily in a smooth way. But if you connect the ends, then you have some structure which you cannot disentangle without cutting that. And such structures can be classified in some way. So what is important when you discuss knots, you somehow don't care about some particular shape they take, whether this is a circle or a rectangular shape. Doesn't matter. What is important is how much they are entangled. And what mathematicians are trying to do is to classify all such knots and then find some ways to distinguish them, to state whether one or the other are indeed equivalent, which means that by some sequence of smooth moves we could transform one onto the other. And here is a beginning of such a classification in this bottom part. So first of all, this is very convenient to project these knots on a plane. So they are like intrinsically three-dimensional, but you can project them on the plane, and then you can always play with them a bit in such a way that you try to minimize the number of crossings which you see after this projection. So of course, the simplest knot is, this is also called trivial knot. This is this one, just like a loop. It has 0 crossings. If you think for a few moments, you can easily convince yourselves that there are no non-trivial knots with 1 or 2 crossings, because they can be transformed into this trivial knot. So if you have something which looks like number 8, you can always twist it, and then you get this trivial knot. So the first non-trivial knot is so-called trefoil knot. This is this one. Then there is one which is called figure 8, and so on. And like the kind of simplest classification is by the number of crossings which you get in such a projection. And there are some also names of these knots denoted by the symbols which you see here. So this capital number, the bigger one, denotes the number of crossings you see, like this 3. And then there is the index, which tells you how many different knots with this number of crossings exists. So there is just one knot with 3 crossings. This is this one, trefoil. One knot with 4 crossings, 2 knots with 5 crossings, and so on. And this number grows very fast. So there are almost 200 knots with 10 crossings, and so on. So you see that it is not sufficient to use just this number of crossings to distinguish different knots, because there are many knots with the same number of crossings. So again, these knots are seemingly simple objects, but they are important because they capture like kind of broad or global aspects of either these curves in space or maybe some other complicated mathematical objects. And that's one reason why mathematicians are interested in classifying them. There are also some cousins of knots which are called links. These are configurations made of several components. Each of those can be knotted. They can also be knotted or linked between themselves. And here are the simplest examples of those links. This is called Hopf link, just 2 unknots which are linked. This is called Solomon link. And these are Borromean rings. This is a very interesting example of a link, because if you look carefully, this is indeed linked. So this is non-trivial structure. You cannot separate those links. But if you remove one, for example, if you remove this green one, then you see that the other 2 can be separated. So each pair of those components is unlinked, but altogether they form some non-trivial link. So this is one interesting phenomenon which happens. And here is a table which mathematicians made. You see here are listed all nodes up to 9 crossings. Here is 9 with index 36. I mean nodes, and then some of those links. Of course, these are kind of simplest nodes and links you can find, but there are many more, and mathematicians would like to have general theory and some general statements which tell you that two links are indeed different. And this is indeed one of the main questions or the main problem in this theory, how to distinguish whether two structures that you consider are topologically non-equivalent. By topologically, I mean that by those sequences of smooth transformations, you can transform one structure to another. So, of course, you see that this thing and this thing are equivalent. You can just untwist this thing and you get that loop. But when you see such a picture, it is already a non-trivial problem. And in fact, this is a very famous picture of the unknot. So you can transform this picture into this loop just by smooth moves without any cutting. But it is very hard to see by a naked eye. And as a mathematician, you would like to have some means to make such a statement that these two structures are equivalent. So of course you can always take a piece of a rope and play with that, but this is not very efficient. You would like to have something more efficient. So these are kind of questions that not theorists ask. And well, I'm not sure how many of you are mathematicians and how much interesting you find such questions, but you will see later on that finding answers to these questions is very useful for other branches of science like physics and biology. But I need to start with this introduction as well to appreciate later achievements. So there are several theorems I will just state. One of them is that you can state whether two nodes are equivalent if you can transform one into the other by a sequence of just three elementary moves, which are called Rademeister moves, which are those given here. So the first one is such that you take a piece of a rope and just make one twist. That's kind of trivial. It operates just on a single strand. Another move is when you have two strands and you can move one over the other. And the third one involves three strands. So there is a theorem that if you have two nodes and one is equivalent to the other, then you can find a sequence made of these three moves which transforms them onto each other. But these Rademeister moves are also not very convenient in a sense. So playing with them would be the same as playing with those pieces of a rope, and it is quite hard. It is not algorithmic. You would have to probably get some additional insights to see how two nodes can be transformed to each other. So mathematicians devise other objects which are called not invariants, which are kind of simpler mathematical objects like numbers or polynomials or functions, which they assign to nodes. And then there is the statement that you can compute this object, so for example, some function, for two different structures, and if you get different results, it means that these structures are not equivalent. And these not invariants are typically quite easy to compute, or at least you can compute them in an algorithmic way. For example, looking at those two-dimensional diagrams and these different crossings, projections, and so on. So you may need sometimes some computational power, but if you have enough computers, you can compute such invariants, and then you immediately distinguish two nodes one from another. And in fact, this minimal number of crossings I already mentioned is one example of such an invariant, because for a given node, what you are supposed to do, you have to manipulate it in such a way that you transform it to the configuration with minimal number of crossings. So this number is certainly an invariant, but it is not very powerful, because as I mentioned, there are many nodes with the same number of crossings, so this is not sufficient to distinguish them. And in fact, this is typical situation in those not invariants. So there are various families of those, but no of those not invariants, which we know now, is perfect in the sense that you can always find two knots which wouldn't be equivalent topologically, but they would give the same not invariant. So this is like a game for mathematicians to define such an invariant which would distinguish all knots one from another, and it would work for all of those. And I will show you a few examples of those invariants. The first one is, in fact, not an invariant of a knot, but of a link, which is called Gauss linking number. And in some sense, it measures how two components are linked all together. So, for example, if you have two unknots, this linking number is 0 in this case. Here it is equal to 1. Here it is equal to 2. And you can guess it from the picture if you are smart enough. But there is also an algorithmic way to compute it. And it is quite simple. So what you do, you have to introduce an orientation on each of those components, like shown by these arrows. And then you have to look at each crossing in a given picture. And you have to identify it with one of those 4 possibilities. And then you assign either plus sign or minus sign, depending on which configuration you have. And then this linking number is equal to number of plus signs minus the number of minus signs divided by half. So we can see that in these 2 examples. For example, here we have 2 plus signs. If you look carefully, you see that these 2 crossings are either of this type or this one. And altogether, we get this linking number being 0 here. And in this diagram, if you compute carefully, you will find that this linking number is equal to 2. So this means that certainly these 2 links are non-equivalent. You cannot transform one onto the other just because these 2 invariants are different. So this is the idea how those knot or link invariants work. In fact, you see that this linking number is also not that powerful, because clearly this link cannot be disentangled into 2 separate pieces, but this invariant is 0, the same as for those 2 unlinked circles. So while you can distinguish this one from this one, you cannot, just using this invariant, distinguish this one from this one, even though by a naked eye you see that this is linked and this is not. So this is why mathematicians are trying to find more powerful invariants. And there is also the statement that you can compute this linking number by doing some double integral, where each of those integrals runs over each strand of a link you consider. So the form of integral is not that important for us, but what is somehow interesting is that this integral is a kind of continuous operation. Typically, when you make integrals, you get the result which is some number which is not integer. But we know that this linking number must be integer, which is kind of follows from these topological constraints. And this is also interesting interplay between like mathematical analysis and topology, that you can get some this is an example where you get some topological answer from the operation which is analytic. In particular, this integral, to make it, you need to know the shape of a link, because you have to integrate over a particular strand. But at the end, the result does not depend on this shape. It just depends on that linking. And again, this is an example of invariant which gives just the number. So this is kind of a simple, we know all what numbers are. And in 20th century, mathematicians found other type of invariants which take values in functions or polynomials. And one of the most famous, probably, of those not polynomials is called Jones polynomial. This is called so because it was found by Jones, a mathematician, and he got Fields Medal for this discovery. So I denote this Jones polynomial by this capital V, and it depends on a knot you consider, so the symbol K stands for a knot. But this is a polynomial in variable which I call T, at least in this slide. And this Jones polynomial can be also computed in some algorithmic way using so-called Skein relation, which is shown here. So this relation tells you that if you take 3 different nodes or links, which are different just in one crossings, so suppose they have many crossings when you project them on a plane, but they are different in one crossing in such a way that in one of those links you have this type of crossing, in another one you have a similar one, but you change the order of what is under, what is over, and in the third node you don't have a crossing but just such a parallel strands. So then the statement is that if you compute these Jones polynomials for these 3 structures, then they are related to each other in some way, in such a way as this relation is telling you. And it turns out that using this relation, you can find this Jones polynomial for any node or link. You have also to add some initial conditions or kind of starting conditions. One of them is that for the trivial node, this relation gives you, this Jones polynomial is equal to 1. And then if you have such a structure that you have some node, and then unlinked unnode, or this trivial node, then the statement is that Jones polynomial for this is equal to Jones polynomial just of this non-trivial piece, and then multiplied by this simple factor. And using that, you can compute Jones polynomials for many nodes. So for example, for the hop link, I have shown it here. We can draw this relation. I focus on this top crossing. So you can see that here this left circle is going under in this case, but here this is going over the right circle, and here they are smoothed. So this is how this relation looks like in this Hopf-Link case. And then you can also notice that this thing, this is topologically equivalent to unlinked circles. You can just separate them. And then we can use this fact from the previous slide. If you have some structure which consists of the unnode and any other node, which in this case is also the unnode, then this Jones polynomial is equal to Jones polynomial for this non-trivial piece, which nonetheless this is trivial not in our case, times this factor. And for the unnode, it just happens that this is equal to 1. This is also this initial condition. So for those 2 unnodes, we get just this result. So from this, we know this answer. And then you can also notice that this thing on the right is nothing but the trivial node for which this polynomial is also equal to 1. So we know the result for this thing and this thing. And then solving in a simple way this equation, we can find Jones polynomial for this Hopf-Link, which if you make a short computation, you get just this result. So this is an example how it works, and you can do that for any other node. And you can play with more complicated structure, of course. If you start with trefoil node, which is here, then I focus on this left crossing. So instead of this one, I replace it either by this thing. And when you look carefully, you see this is the trivial node. So Jones polynomial for that is equal to 1. And on the other hand, here when I smooth it, I get the structure which is just the Hopf-Link for which we computed the Jones polynomial in the previous slide. So again, if I know the result for this thing and this thing, I can solve it and then find what is the result for the trefoil. So you see that doing this kind of algorithmic computations, we get some functions. And then if we do such a computation for 2 different structures, if we compare the result, it is very easy to compare polynomials or functions. We can determine whether they are equivalent or possibly not equivalent. And even though this may sound a bit simple, at least the way I'm presenting that, this is quite an important achievement. As I mentioned, in particular, Fields Medal, which is like the most important prize in mathematics, has been awarded for this discovery. So I don't know, maybe there are some questions at this stage. Or if not, then I will say a few words about history. Okay.
Can you go all the way around? So can you came up with polynomial and try to figure it out if it makes note?
That's a good question. In general, not. So there are 2 problems. One of them is that not all polynomials are polynomials assigned to some nodes. That's one problem. But the other one is the one I mentioned before, that there could be 2 nodes which are not equivalent, but they give the same result. And then this polynomial doesn't distinguish them. You cannot say, just looking at the polynomial, which knot you started with. So, but in general, that could be a good question to find a set of polynomials which are not invariant. It's not that obvious. So there are, of course, big tables with these polynomials now for all knots up to whatever, 15 crossings or so. But if you write some high order polynomial, it is not easy to state whether it corresponds to some knot. Okay, yeah?
Is there some finite set of different characteristics that would identify the knot uniquely?
Well, apart from the knot itself, it doesn't seem so, or at least we don't know. So as I said, all knot polynomials, or all those knot invariants which you know so far, cannot distinguish all knots from each other. So this is...
You use all of them at the same time.
That's right. Yeah. So I mean, there are some, I don't want to go into details, there are some speculations that some class of these invariants would be sufficient, but then they are, in a sense, you need infinite number of information anyway to compute all these invariants which might distinguish some knots. So we don't have any simple way which would do that. Okay, so I will say now a few words about history to show you that these knots, well, of course they are a branch of mathematics, but they are also related and inspired scientists in other disciplines. And more systematically, people started looking at those knots in the 19th century. One of the first mathematicians was Gauss, who devised that linking number. And then Kelvin had an idea that atoms, I mean these chemical atoms, when people didn't know their structure yet in the 19th century, he thought that they might arise as different knots which are made in ether. So this was a theory for some years, then of course it was disproved, but for some time it was an idea that these knots might play a role in nature. And then in 1895, as you see, another mathematician, Tate, made a knot table with knots up to 10 crossings. So this was quite a non-trivial achievement without computers and so on. He had to sit on a piece of paper and draw all these 200 knots and be very careful, checking whether two are equivalent or not. And then one breakthrough came in 1928 when Alexander found one of first knot polynomials, which is now called Alexander polynomial. But in some sense it is simple. In 1984, so it was much later, almost 60 years later, Jones found that Jones polynomial that I mentioned. So you see that this is quite a recent discovery, like 30-something years ago. And soon after, another version, more complicated polynomial, but somehow related to this Jones, was found, which is called Humphrey-PT, where Humphrey and PT stand for initials of mathematicians who found that. In particular, P stands for Przytycki and T for Traczyk. They are two Polish mathematicians, and this is Józef Przytycki who found that. So this is also quite an important discovery. In 1989, it was found that these knot polynomials are related to quantum field theory and to physics in some way, which I will describe briefly in a moment. But this is also a very important result which brought these two fields somehow together, like theoretical physics and knot theory. And in 1999, which is like 20 years ago, another breakthrough came, and Kovanov, also a mathematician, defined something which is called knot homology. This is more complicated type of invariant. If some of you are mathematicians, then you might have heard of homology theory, and he found some way to define such theories and assign them to knots, and they form more powerful knot invariants. And I already mentioned that this mathematician Jones got Fields Medal for finding Jones polynomial. Also, two other scientists got Fields Medal, Edward Witten, who is a physicist in fact, and Maxim Kontsevich, a mathematician. They all got this Fields Medal for some work related in some way to knot theory. So this somehow shows that this is an important field of mathematics. But as I'm trying to convince you, it's not only a field of mathematics, because recent Nobel Prizes in 2016 were given by some work in physics and chemistry which makes contact with topology and knot theory as well. In particular, this picture is from the official announcement of the Nobel Prize in 2016, and you see that it looks like the Hopf-link. These are just some chemical compounds which make a Hopf-link. So you may immediately see that all this mathematical machinery developed over the past century and so on must be important in analyzing those physical or chemical systems. And after this kind of introduction, I'd like now to focus and tell you a few words about this relation to quantum field theory and quantum physics. So first of all, now I don't know how many of you are physicists, but even if you are not, you might have heard of so-called classical physics, and probably you might have heard of the statement that in classical physics, all events seem to be deterministic. Namely, there are some equations which are called equations of motion. If you solve them, you can predict how a given system behaves. So if you have a particle at point A, you solve equations of motion, and then you find that it will reach the point B according to following some trajectory and so on. And in quantum physics, situation is more complicated because you have to take into account all possible ways of connecting, for example, 2 points you are interested in, and then what you can compute is just the amplitude or some probability of going from point A to point B. Each of those different ways of reaching point B gives some contribution to this final amplitude. So I'm not going into much more details, but if you are not a physicist, that this gives you more or less the idea what quantum physics is. You have to think of all possible configurations or trajectories connecting to states. And it turns out that there are some quantum theories which are called topological quantum theories, or more specifically what I am interested in, they are called topological quantum field theories. These are theories in which those amplitudes depend only on topology of some system you are considering, or topology of states in a system. And there is one example of such theory where you can consider a kind of particles which move along trajectories which are knotted. And then the statement that this theory is topological is the statement that the amplitude of moving along some trajectory depends only on topology. So in this case, it depends on the way in which this trajectory is knotted, and not on a particular shape of that trajectory. And this work of Witten, which I mentioned, which he found in 1989, is the statement, well, he found some example of this topological quantum field theory such that these amplitudes assigned to certain kind of particles which move along some knotted trajectories, these amplitudes reproduce those knot polynomials that I mentioned before. For example, Jones polynomial. So this gives completely different viewpoint on those knot polynomials and the whole knot theory. In particular, the skein relation that I mentioned before, it turns out that it has some physical meaning, and this is simply a relation in some two-dimensional Hilbert space. So if you are a physicist and heard of Hilbert spaces before, then it may happen that Hilbert space you consider is two-dimensional, and that skein relation I had before gives you some relation in that two-dimensional space. So of course, I would need much more time to explain details of this statement, but you see that this gives kind of physical perspective on those mathematical theory. And I have one more slide, maybe more for physicists, where some formulas appear. So it may not be trivial for you if you're not a physicist or a mathematician, but nonetheless, let me show that. So this is so-called Lagrangian of this Chern-Simons topological quantum field theory. And it involves so-called gauge field A. So in general, you might think of such a gauge field, so the symbol A, as something which in case of electromagnetism would capture properties of electric and magnetic fields. But in case of electric and magnetic fields, we also can formulate their theory in terms of some Lagrangian or action. So we write similar formula, but it is somehow different. the main feature of this formula is that it does not depend on the metric of the space which we consider. So this is written in terms of purely in terms of differential forms, and no metric arises in this expression. Essentially, this is the reason why the final outcome, when you compute quantum amplitudes, like in this line, these amplitudes do not depend on the matrix, so they depend only on topology of the trajectory you considered. And now this expression denotes roughly what I mentioned before. So this integral of this capital D means that you are supposed to consider all possible configurations of those gauge fields. They all contribute in some way to your quantum amplitude. You have some measure which is exponent of that classical action. And then this thing in the bracket, essentially this is exponent of integral of integrating this gauge field along some trajectory. So at the end, this result gives you some function of the parameters in this expression, and it turns out to be equivalent to this Humphrey PT polynomial that I mentioned before. If you think, or if you look carefully, this integral depends on this symbol k here. This is so-called coupling constant, which appears here in this symbol q I had before. And this n appears in SUN gauge group. So essentially, there are two parameters k and n, and those two symbols or those two arguments of Humphrey PT polynomial, which are commonly known as a and q, can be expressed in this k and n. So this is how you can get this standard knot polynomials from quantum field theory and quantum physics. And furthermore, Jones polynomial is a special case of this Humphrey PT polynomial, which you get for this number n being equal just to 2. And Alexander polynomial is also yet another special case, which you get for a equal to 1. So that's general idea how you make this connection. And this work gave a lot of impact and inspired many other works. Now this paper by Witten from 1989, it has more than 5,000 citations, so it somehow shows how important it is. And let me also mention that this topological quantum field theories, they are interesting in themselves, they are interesting for mathematicians, and also they are interesting for physicists, because you can think of them as kind of toy models for other more complicated quantum field theories. And currently we know that it seems that all forces in nature and all physics can be reduced to like two kind of pillars, in fact two kind of field theories. One of them is just theory of relativity formulated like 100 years ago by Einstein, and standard model of elementary particles, which is a particular version of quantum field theory. This is quantum theory. I mean, standard model, this field theory behind that has quantum formulation. We don't know quantum formulation of general relativity, but this is one dream of physicists. They would like to find quantum theory of gravity that you might have heard of. That's one thing that they would like to find. And also they would like to find some way to unify these two types of theories. So if you try to understand not necessarily particular processes which happen in nature, but like mathematical structure of these theories, then it is very useful to look at those simpler models of topological quantum field theories and understand some phenomena which appear in those cases. So again, let me stress that topological quantum field theories, TQFT is the acronym I use sometimes, are some, in a way, similarly to knots. They are seemingly simple theories, but nonetheless they are complicated, and they capture some essential features of more complicated theories which are good to understand before considering those more complicated theories themselves. And physicists are trying to unify these two theories. There are various ideas, and one of the important and quite, let's say, successful idea is string theory, which in some way tells you, at least qualitatively, how this theory of relativity and theories behind standard model could be unified. And I'm mentioning of that because there is also a topological version of this string theory, which is simply called topological string theory. And within that theory, you can formulate also various statements known from knot theory. So here I briefly described how you can engineer certain system of so-called D-branes, which are higher dimensional objects in string theory, which enable you to engineer knots. And then using techniques of string theory, you can, again, reproduce known knot invariants. And also, people found new knot invariants, which are not known before to mathematicians. So I will not go into too much details, but let me just say that this knot theory system I mentioned before, it happens just in three-dimensional space. So that three-dimensional space is this S3 here. And string theory, as you might have heard, requires having 10 dimensions. So we need to embed these 3 dimensions in 10-dimensional space somehow. And we do that in such a way that we split, first of all, these 10 dimensions into 4-dimensional space-time, which morally are 4 dimensions where we are supposed to live. And then some 6-dimensional space, which in this particular case we take to be cotangent bundle to this S3. And then we can engineer some knots in this space, 3-dimensional space S3, by considering, as I mentioned, some system of so-called branes which intersect just along 1-dimensional curve. And then we can find so-called effective theory which describes what happens in this case from the viewpoint of this 4-dimensional theory and particles which would live in this 4-dimensional theory. We can in some way count these particles which would effectively arise in those 4 dimensions, and it turns out that this counting provides new types of knot invariants. And of course, more details would be necessary to explain how it happens, but I will just show you one result which follows from such considerations, which is quite a non-trivial statement. So at the end, I wish to count some particles in 4-dimensional space, and I get some result for that counting, which is given by this formula. And what is non-trivial in this formula is that the result is supposed to be integer, but this formula is just a combination of Newton symbols. So you know that Newton symbol, this is just ratio of some factorials, but this is integer number. And we take a combination of these integer numbers with some signs. Here is this symbol mu, this denotes so-called Möbius function. This is definition, what this function means, but this takes value only 0, 1, or -1. So this summation is a combination of Newton symbols with plus or minus signs. So for sure, this is integer number. But then all that is divided by r squared. And we get the statement that this ratio of this sum divided by r squared is also integer, which gives us some statement in number theory on the other hand. Because this is non-trivial statement. If you take some integer number, it is not necessarily divided by this parameter r here, on which this expression depends. So we can get also this type of statements from some string theory consideration. So this might be interesting for those of you who are interested in theoretical physics or mathematics. And I'm afraid I cannot explain more details about that. I might answer some question if someone would have at this moment. And if not, I would still like to spend maybe 3 minutes. I'm not sure how much time I have. 2 minutes, OK. So I tried at the end to... Sure. So at the end, I'd like to show you some more down-to-earth application of knot theory, not related to string theory, but also to physics, but another branch of physics, which is biophysics. And in particular to proteins, because it turns out that, as I mentioned in the beginning, you find knots everywhere. You can find them also in proteins. So you might have heard also that proteins are like long chains made of amino acids, as shown here. They form some non-trivial structures like shown in this picture. And you might wonder whether such a structure can be knotted. This is a non-trivial question. For many years, people thought that such proteins cannot be knotted. But in 1994, as you see, the first example of such a knotted protein was found, and from that time people started to looking at searching for knotted proteins, and it turned out that there are many of those. This is also some research I've been involved in. Now we know that around 1% of all proteins form knots, but there are many proteins, so this 1% is in fact a lot of structures. There is just one subtlety that these proteins have open ends, so to define a knot you have to connect these ends in some way, but there are some ways to do that, and quite often you can do that in some unique way. And here we have some examples. So these are pictures of knots. They look complicated, but if you simplify these pictures to kind of just simplest configuration, that you can see that indeed this topologically non-trivial structures arises. So this is example of some protein which forms this trefoil knot. This one forms figure 8 knot, and this forms one of those knots with 5 crossings. So you might wonder how to identify these structures, and then it turns out that these knot polynomials, which are explained how you can find them before, are very useful to this end, because when you look by a naked eye on the structure, typically those proteins consist of several hundred of amino acids. It's just impossible to see whether it is knotted or not. But then you can take such a structure. We know where these amino acids are located in three-dimensional space from some, for example, crystallographic experiments. And then you can put it on a computer, simplify. If you have this type of picture after simplification, you can compute a knot polynomial. And typically, these knots are not very complicated. So these knot polynomials that I mentioned before, like Jones or Humphrey, are sufficient to distinguish them. And we have made a database of such structures. It is called NotProt, and there is a website address on top. And all knots which are found in proteins are assembled in this database. And this is also regularly updated. So every week, there are new protein structures uploaded to some big database with proteins, which is called Protein Databag, PDB. And then automatically the structures are tested by this NotProt website. And if they are knotted, then they are also assembled into this NotProt database. And here are some functions. So in this database, we have different type of nodes, we have different classifications, and so on. I will not explain details now, but you can go into this website and look at that. If you find some particular protein, you can look how it, you can see how it looks like in a graphical picture, but we also have some graphical presentation of where the knot is located and some other details of that knotting. And one of the things that biophysicists are trying to do is to understand what is the function, what meaning in, like for life, all those knotted structures have. But they are convinced that they should have, because it cannot be accidental that such structures have been created and they were not eliminated by evolution. So this is kind of hot topics, and there are many groups these days in the world looking at those knotted proteins. So to summarize, I hope I convinced you that this knot theory is an interesting branch of mathematics. Its mathematical aim is to classify knots, and then you can use various classifications and tools devised by mathematicians in other branches of physics, chemistry, of biology. And let me also stress that this type of research, including both string theory and quantum physics, and also mathematics and biophysics and proteins, is something that we do with the group at the Faculty of Physics, University of Warsaw. On the top, this is also the website of the group I am head of, and this is this picture of our group. If you look carefully, I must say this is quite unfortunate, but you see here are only guys and no women, so we encourage in particular women to get involved in this research and join us. And moreover, I use this occasion to advertise another activity I am involved with, which is more related to science popularization. This is called Ask a Physicist, or Zapytaj Fizyka. This is in particular a series of lectures which we organize like once every month or every 2 months. We had one lecture yesterday, so this is why I had to fly to London just today. It was a lecture by one professor from Stony Brook who was talking about neutrinos. Another lecture will be in April. This is the website where you can look at as well. And yeah, this is one of the activities of our department in science outreach. So I think that's all I wanted to say. Thank you.
Thank you.